Galvanic cells is going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. I'll be sure to leave a link in the description below so you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the rest of this school year, so if you want to be notified every time I post a new one, subscribe to the channel, click the bell notification. All right, galvanic cells. Now, another name for a galvanic cell is a voltaic cell, but most of you are probably going to hear it more likely to be called a galvanic cell than a voltaic cell, but same diff. They're totally synonymous. Treat them as the same. And it turns out that is one of two primary types of electrochemical cells. So there are two main types of electrochemical cells. The galvanic cell, again, also called a voltaic cell, that's one. And then the electrolytic cells, where electrolysis happens, is going to be the second. And the last two lessons in this chapter, we'll spend a little more time talking specifically just about those electrolytic cells. But I've got to bring this up. If we're going to talk about galvanic cells, we really got to give the bigger context in which they exist. And they're one of two major types of electrochemical cells, and the second is the electrolytic. And we'll compare and contrast them a little bit, and then spend a lot more time definitely talking about the galvanic cells. So if you look at these two major types of electrochemical cells, the biggest difference between them is that your galvanic cells are spontaneous. So there's a spontaneous reaction going on, whereas your electrolytic cells involve a non-spontaneous reaction. So, and again, up until this chapter with thermodynamics, the biggest way we knew a reaction was going to be spontaneous is we took a look at delta G. And when a reaction was spontaneous, delta G was negative, whereas when a reaction was non-spontaneous, delta G was positive. Well, it turns out for redox reactions, there's a second way that's often much more common measure for figuring out if a reaction is spontaneous, and that is your voltage, except the voltage is kind of like the common name. It is the EMF, or cell potential, and EMF stands for electron motive force, or cell potential. And that's the same thing that you're more likely to understand as voltage measured in volts. And so it turns out it's abbreviated E cell, either with a Greek letter epsilon here or just a capital E. And E cell is your, again, cell potential or voltage. And it turns out when it's positive, when you got a positive voltage, so that's when a reaction is spontaneous. And when you've got a negative voltage, a negative cell potential, that's when the reaction is non-spontaneous. And so it turns out that when delta G is negative, E cell will be positive. They always have the opposite sign. When delta G is positive, E cell will be negative. It turns out they're mathematically related, and we'll see that in a couple lessons down the road in this chapter. All right, so in a galvanic cell, you've got a spontaneous reaction, and that spontaneous reaction is used to produce energy in the form of electricity. So we're using a spontaneous reaction to generate electricity. Whereas in an electrolytic cell, these actually consume energy instead. So we're going to actually have to hook these up to a power source to force a non-spontaneous reaction to happen. So if you look at these, which of these could function as a potential battery and produce energy? Well, that's your galvanic cells. Your galvanic cells are your batteries. When your battery is running in its forward spontaneous direction, so it's acting as a galvanic cell. Now, when you're recharging your battery, on the other hand, what you're doing is you're running the spontaneous reaction exactly backwards, though, in the non-spontaneous direction to recharge it. And truth be told, when you're recharging a battery, it's actually functioning during that recharging process as an electrolytic cell. But most of the time, that's not what we're going to be referring to when we talk about electrolytic cells. We'll find out that electrolysis is often used to produce certain elements, like industrial production of chlorine. And we're going to make chlorine here, or at least talk about the example where chlorine can be made. In industrial, the biggest way we make chlorine industrially is through electrolysis via an electrolytic cell. And so it turns out very commonly electrolytic cells are used to produce different elements, like elemental chlorine or elemental sodium or things of a sort, as we'll see in a little bit for an example. All right, so in any electrochemical cell, you're always going to have two electrodes, and these electrodes are going to be typically made of metals because they need to conduct electricity, and we're going to suspend them in a solution in one way, shape, or form. And so these electrodes have names. So one of them is the anode, and the other is the cathode. So, and it turns out that the anode, by definition, is always the site where oxidation takes place. The cathode, by definition, is always the site where reduction takes place. And so if you kind of take a look at anode and oxidation, they both begin with a vowel. Cathode and reduction, they both begin with a consonant. So, and it turns out when you're diagramming out a galvanic cell, you are always supposed to put the anode on the left and the cathode on the right. Now, I say you're always supposed to do that. That's like the formal, these diagrams are a formal thing, and whoever made up the rules, that's what they said. However, not all instructors know this and don't take the time to do this, but it is super important because sometimes how they define certain calculations, they talk about the left and the right. And by left, they really mean anode, and by right, they mean cathode. So that's why this is really formal. So, however, if your instructor isn't aware of this, just run with it. All right, same thing over here. So anode on the left, cathode on the right. So, and the anode is still the site of oxidation, and the cathode is still the site of reduction. That hasn't changed. All right, so if you look then, your anode and your cathode here. So anode is where electrons are lost, i.e. oxidation. Cathode is where electrons are gained, i.e. reduction. And so it turns out that electrons are going to be transferred from the anode to the cathode, from where they're lost to where they're gained. And that's what this wire connecting the two electrodes is for. It is for the transfer of electrons from the anode to the cathode. And so we see here that electrons are going to go from anode, if I can spell anode, that would be great. Anode to cathode. And that is true in the electrolytic cell as well. Again, electrons can only go from where they're lost to where they're gained. And so by definition, I still can't spell anode. Electrons are traveling through the wire from anode to cathode. So electrons always travel through the wire from anode to cathode. It's important that you realize it's also through the wire. It's often something we'll test you on. So electrons travel through the wire from anode to cathode. And if you want to remember, like, it goes in alphabetical order, like anode to cathode, A to C, great. But you have to know that the electrons go from anode to cathode. Now the difference though is whether that's the spontaneous way they want to go or it's the non-spontaneous direction. So, and over here with the galvanic cell, that's the spontaneous direction. That's where the electrons want to go. And the electrons being negatively charged want to get away from the electrode that is negative and go towards the electrode that is positive. Now, a little tongue-in-cheek here, because the truth is the electrodes themselves are not charged in the way that you'd think. So, but it turns out the negative and the positive actually refer to the cell potential. And a negative cell potential means a lower cell potential, and a positive means a higher cell potential. And so it turns out that electrons do want to go this direction. So it turns out everything in the universe wants to lower its potential energy. If I let go of this marker, it goes down because it lowers its gravitational potential energy as it travels down if you've taken any physics. So it turns out that, again, the spontaneous direction for electrons is to go from lower potential to higher potential. And that seems super tricky because the truth is when an electron is at lower potential, it has higher potential energy. Add that energy on the end. So it's weird because it turns out that the term potential is really defined for positive charges. And it turns out positive charges have higher potential energy when they're in an area of higher potential. And positive charges have lower potential energy when they're in an area of lower potential. But it's the opposite for electrons. Electrons have higher potential energy in an area of lower potential, lower voltage. Electrons have lower potential energy in an area of higher voltage. So higher potential. So it's really super tricky. So the electrons are still going from higher potential energy to lower potential energy, but they're going from lower potential to higher potential. Cool. I just want to make that clear. It's not super duper important. I just didn't want to confuse anybody. But the big thing here is that you got to realize that the anode is negative and the cathode is positive. So in our galvanic cells, and again, for me, it's just easiest to remember by thinking of them as charges, even though this is not really charges, and that electrons being negative want to get away from the negative electrode and are attracted to the positive electrode. But again, it's not what it really means. I just wanted to give you the truth So, but that's usually how I remember it as well, FYI. Cool, in the electrolytic cell, it's the exact opposite. So it turns out it's now the anode that is positive, and it is the cathode that is negative. And notice the electrons would actually prefer to go the opposite direction. The spontaneous direction is in the other direction. That's why we're forcing a non-spontaneous reaction to happen. That's what we need a power source for, whether we plug it into the wall or plug it into a battery. So we need this plugged into a power source because it's going to pump the electrons uphill energetically, so to speak. All right, so let's put that up here as well. So the anode was positive and the cathode negative, but it's the opposite over here. Now it's the cathode that's positive and the anode negative. Cool. So again, electrons are pumped, or we shouldn't say pumped. Electrons travel from anode to cathode through the wire in both types of electrochemical cells, the galvanic and the electrolytic. What is different is the sign on each. In the galvanic cell, the anode's negative, the cathode positive. In the electrolytic cell, the anode's positive, the cathode negative. You should realize that distinction. Okay, so let's talk about a specific reaction now and finish off this lovely diagram of the galvanic cell for this one down here. So it turns out under standard conditions that this is a spontaneous reaction. We'll learn how to calculate cell potentials for this reaction in the next lesson, but suffice it to say that under standard conditions, this reaction right here has a positive cell potential, a positive voltage, and therefore a negative delta G, and is spontaneous. So I chose it wisely. And if we kind of identify some things here, so here we've got copper 2+ turning into copper. Notice its oxidation state is going down, and that's why they call it reduction. And so copper 2+ is being reduced, which means that's what's going to take place at the cathode. In a galvanic cell, we actually separate the reaction, the oxidation and the reduction half reactions, into two separate compartments. That way the electrons have to travel through the wire from one to the other. And while they're traveling through that wire, they have the potential to do work. Like, you might have a toaster plugged in that wire in the middle of it, and as it travels from anode to cathode, downhill, if you will, energetically, it runs through the toaster and it gives off a bunch of heat. And things of this sort. So the idea is that if these weren't separated into two compartments, well, then you wouldn't have electrons traveling through a wire. It would just all happen within one solution. And we want the electrons to travel through the wire because that's when we have the chance to power our devices. All right, so we've got two half cells here for this galvanic cell for that reason. And in this case, the copper 2+ to copper, that's going to happen at the cathode. It's going to gain 2 electrons to turn into copper. And on the other side, zinc going to zinc 2+, that's the loss of 2 electrons. The oxidation state's going from 0 to +2. It's not going up, it's going down. And so now we've identified the half reactions happening at each of these electrodes. Now we said that these anodes and cathodes, these electrodes, have to be able to conduct electricity. And typically, as long as one of the species on the reactant or product side of your half reaction is a solid metal, which is therefore capable of conducting electricity, that's what it's going to be made of. And so in the anode side, we have zinc solid metal on the reactant side, and that's what the electrode itself is going to be made of, solid zinc. On the other side, we have a solid metal as copper. It's on the product side this time. It doesn't matter if it's on the reactant or product side. As long as we have a solid metal that's capable of conducting electricity, that's what we typically are going to make the electrode out of. And so we'll have solid copper metal. Now, while you have the solid metals as the electrodes, you typically then have to put the corresponding aqueous ions, in this case copper 2+ ions or zinc 2+ ions, dissolved in the solution around it. So under standard conditions, these concentrations would both be 1 molar concentrations. They'd already therefore be in the solutions. So if we diagram this out in kind of standard conditions, we're going to have some zinc 2+ down here. We're going to have some copper 2+ down here. And my question for you is, well, how did I get zinc 2+ and copper 2+ in here? Did I just pour a bottle of zinc 2+ into this one and pour a bottle of copper 2+ into this one? Well, it turns out there's no such thing as a bottle of zinc 2+ or a bottle of copper 2+. The way you get them in there is you have a bottle of their corresponding salts, some sort of copper salt and zinc salt. And so the one I'm going to choose here just for simplicity's sake is zinc sulfate, and over here copper sulfate. And so initially, for every copper, you have a sulfate. And for every cation, you have an anion, and it's balanced, 1 to 1. Same thing over here with the zinc sulfate. +2, -2, it's a 1 to 1 ratio. And so the sulfates are in there. They're not going to do anything, but there was, I had to use some sort of salt to get the zinc ions and the copper ions in the solutions. They couldn't just exist there without a corresponding anion in the solution with it. So I just want to make you realize that'll be important in a minute. All right, so we're not done yet. There's one big key component to this that we haven't talked about, and it turns out we need to connect these two solutions. If you don't connect them with this bridge right here, you have a dead battery. That bridge is super important, and we're going to fill this bridge with salt. So it's going to be some sort of aqueous salt, often suspended in like a gel-type matrix, but capable of having ions flowing through it. And so I'm going to stick some sodium ions in there and some nitrate ions in there. So I'm using aqueous sodium nitrate in what we call the salt bridge. So it's a bridge full of salt, so they named it Salt Bridge, appropriately named. Now, the whole purpose of this salt bridge is to keep these solutions neutral. So it turns out over the course of time, these solutions are going to want to end up with opposite charges if we didn't have this salt bridge. And that's not good. Putting a bunch of positive charges all close together, they repel each other. They don't want to be together. That would be non-spontaneous. Same thing if you put a bunch of negative charges together. And so if we get a buildup of opposite charges in these solutions, it's actually going to make the reaction non-spontaneous. And actually, it turns out you'll never get the chance, because if that's the case, if you don't have this salt bridge, you have a dead battery. It's not going to function at all. And so it turns out, it makes it easy to memorize that the anions in that salt bridge are going to travel into the anode compartment, and the cations in this salt bridge compartment are going to travel into the cathode. We got to talk about why for a minute. Well, if we look at the anode side, we've got zinc turning into zinc 2+. And so what that really means is the zinc metal itself is turning into zinc 2+. It loses 2 electrons in the process, and it sends those electrons to the other side, and those electrons sit on the surface of the copper, just waiting for a copper ion to bump into it. And when that copper ion bumps into it, it gains those 2 electrons, turning it into copper metal. And it turns into copper metal when it's in contact with more copper metal. And so it actually plates out, we say, on the surface of the electrode, and this electrode is going to get fatter over time. So this electrode is actually dissolving away into the solution as it turns from zinc metal into zinc ions, whereas this one's going to be getting fatter as we make more and more copper solid in that half reaction. And so we like to say that the anode is losing mass in this case, and the cathode is gaining mass. And that's really common for a lot of galvanic cells. Not everyone, we'll talk about an exception a little bit, but for most galvanic cells you're likely to encounter in this class, the anode's going to lose mass and the cathode's going to gain mass. And the way you verify that is that you just look in your anode half reaction and be like, yep, I have a metal being consumed. It's on the reactant side. And on the cathode side, yep, I have the solid metal being produced. It's on the product side. And that's how you know the anode's losing mass, the cathode's gaining mass. And again, we'll see an exception here shortly. All right, so once again, looking at it now, not following the metal, but follow the ions. On the anode side, we're going to be producing more and more and more cations, zinc cations. Well, again, before this battery's turned on, you have equal number of zinc and sulfate ions and the solution's exactly neutral. Well, if you start producing more and more zinc ions, the solution would start to get positively charged. That's why the anions are flowing into the anode. So again, it's easy to remember. Anions flow into the anode through the salt bridge. So anions are flowing into the anode to keep the solution neutral. Sometimes we'll say to maintain electrical neutrality. On the other side, we have the exact opposite thing. Now, instead of making cations, we're using up cations. We're consuming cations, and so their concentration is going to go down. And so now we'd have excess sulfate ions, and this solution would tend to want to get negatively charged. Well, that's why the cations are flowing into the cathode compartment to keep that solution neutral. And so again, the whole role of the salt bridge is to maintain electrical neutrality in the solutions in the half cells. Cool, you should definitely distinguish that electrons are flowing through the wire between the two half cells, whereas it's ions flowing through the salt bridge. Don't get that backwards. So electrons flow through the wire, ions flow through the salt bridge. All right, now if we compare and contrast this to our diagram of our electrolytic cell, well, electrolytic cell, we're not going to be producing electricity, we're going to be using it up. And so we don't actually need to split these into half cells so that we get a chance for the electrons to do work, because we're not going to be able to do any work over here. We're not producing any energy, we're consuming energy over here. All right, so in this case, we're going to look at the reaction of liquid sodium chloride. They call it a molten salt. We'll study that more again in the last 2 lessons of this chapter. And it's going to be converted into sodium metal and chlorine, elemental chlorine. And so it turns out we're starting with sodium in the +1 oxidation state. And we're starting with chlorine in the -1 oxidation state. And then we're producing elemental sodium and elemental chlorine both in their 0 oxidation states. And so in this case, you're going to have Cl- turning into Cl2 and losing some electrons in the process. So if we take a look at this, we got 2 Cl- go into Cl2 plus 2 electrons. Loss of 2 electrons, it's oxidation. And then those electrons get transferred through the wire. They get really pumped through the wire by our power source. And over there, we're now going to have the sodium ions that we started with. So gaining those electrons to turn into sodium metal. And depending on how hot we had to heat this to melt the sodium chloride, that sodium metal might be solid liquid gas. Notice I didn't put the phases here because you might not always be in a position to predict them based on how hot this is. And chlorine's most likely going to be a gas. In fact, I can't envision anything else because regardless of how hot I heat it, it's a gas at room temp. But the sodium, probably not going to be solid sodium, probably going to be liquid sodium under such conditions where I'm doing electrolysis with a molten salt. So I didn't put the phases there because I don't think it's fair to have you predict the phases either. So I just told you what the phases were, but I don't expect you to be able to predict phases in just such an electrolysis reaction. Cool, and that's kind of how it works. Notice there's no salt bridge over here. So, and notice also, it's convenient that the chloride ions, which are negative, are attracted to the electrode that is positive, and the sodium ions that are positive are attracted to the electrode that is negative. And again, these don't really mean charges, but again, we're following a pattern here that they are useful, and it is helpful to kind of think of it that way, even though that's not technically what's going on. It's really about potential rather than charge, but it might help you remember what's going on here. But notice, anions are oxidized at the anode, cations are reduced at the cathode. Makes it easy to remember. And again, we will study electrolysis and electrolytic cells in more detail in the last 2 lessons in this chapter. So if you didn't get a lot here and get it all down here, you will definitely get the chance. We'll go into more detail later. I just really wanted to contrast it for the galvanic cell, but this lesson's really about the galvanic cell. All right, so one last thing I want to talk about, and that's what we call an inert electrode. So an inert electrode is when you use an electrode that's not participating in the reaction. Notice here, the electrode is a reactant in the reaction. Here, the electrode was a product of the reaction. It's definitely participating in the reaction in both cases. But that's not always going to be true. So if we took a look at, let's say instead of having the copper half reaction going on in this electrode, let's say we swapped that out with the following half reaction. So here we're going to reduce hydrogen ions to hydrogen gas from the +1 oxidation state to the 0 oxidation state. That is a reduction. So and it turns out this is called the standard hydrogen electrode, or the SHE for short. So we'll bring him back up in the next lesson. But this is the standard hydrogen electrode, and we have a problem here, is that there's nothing in the reaction that can serve as an electrode. I need a solid metal that can conduct electricity. Well, I don't have a metal, and I definitely don't even have a solid. I have aqueous hydrogen ions, and I have a hydrogen gas. Can't use either one of those as an electrode. So in this case, we have to use what's called an inert electrode, and platinum is pretty common. And so what we do is we make the electrode out of platinum, and the hydrogen ions gain the electrons from the electrode, turning into hydrogen gas. But the platinum is there just to deliver and pass on the electrons. It doesn't participate in the reaction. None of the platinum gets consumed. No more platinum gets produced. And so in that case, when you're using an inert electrode like this, notice you're not producing any solids. You're not using up any solids. And so the electrode itself is not going to gain or lose mass. And so we said earlier that in most galvanic cells, you're likely to encounter the anode's going to lose mass, the cathode's going to gain mass. The exception is when you're using an inert electrode. An inert electrode is not going to gain or lose mass at all. So I just want to make sure you've seen an example of an inert electrode. Now, if you found this lesson helpful, a like and a comment, let me know. Are pretty much the best things you can do to support the channel. And if you're looking for practice or any extra resources on your general chemistry, take a look at my general chemistry master course. I'll leave a link in the description. Free trial is available. Happy studying.